Hey, this is Math 8, Unit 6, Lesson 4, fitting a line to the data. Let's look at some scatter plots as a whole is the idea here. So first off, we start with a section called Predict This. And it says, here's a scatter plot that shows weights and fuel efficiencies of 20 different types of cars. So that is how much it weighs and how efficient the fuel is, talking about kind of usually in miles per gallon, how many miles you get per gallon of fuel. If a car weighs 1,750 kilograms, would you expect its fuel efficiency to be closer to 22 or to 28, and explain your reasoning? So the idea here is that we have some data of 20 different cars, right? And you can see there's somewhat of a trend here for what tends to happen, right? The lighter the car is, 1,000 pounds over here, the better the gas mileage, 30 or so, seems to be. And we really would say, it seems like that the heavier the car is, the less fuel efficiency you end up getting. So if you were to take something like a car that said 1750, a car that weighs 1750 is here, right? And so that would mean it would be somewhere about here where we would expect that it would probably find its fuel kind of capacity at. What would it be at? Now in this case here, if we're looking at someplace right there, we would draw a line across and say, well, where are we at? Well, we're somewhere between 21 and 22 if we use this as a line for about where it would end up at. So 1750 is somewhere near 22, a little less than 22. So we would probably say it's going to be closer to 22 miles per gallon than it would be 28. You see, 28 would be up here. And so if that car had a weight of 1750 and its fuel efficiency was 28, it'd be really far away from that line. In fact, realistically, if it was a 28, we would expect if it got 28 miles per gallon, we'd expect that car to actually weigh more like what? 1,250 kilograms. So this makes the most sense to be closer to 22 than to 28. Okay? And so when we're looking at this here, basically we have a couple things. We have our independent variable here. This is the part that's not changing, right? The weight is independent, but based upon that weight, you end up with a number that is dependent upon the weight. So these two numbers, or these two values, are related to each other in that way there. There's a connection between weight and fuel efficiency, at least according to the data, because we can draw a type of line there. Okay? Let's look at the next activity. The next activity, we're going to begin with actually a picture. So I'm going to pull out my book here, and we're going to zoom in a little bit on this picture. It's not a great one here, but we can see a picture here with three types of diamonds there, right? We have a big one, a medium one, and a smaller one. Three different types of diamonds here. So when you look at these diamonds, really what you want to question is which one do you think would have the highest price? Which one do you think you have to spend more money for? Well, do you think the smaller one? Probably not. Most likely you're going to spend more money on the larger one because it tends to be bigger, and bigger with diamonds sometimes is better. Okay? So that one probably has the highest price based upon the size, and that one probably has the lowest price, again, based upon that size. Now the reason that's important is that in diamond world, oftentimes the value or the price of a diamond is based upon its weight, which is measured in what's called a carat. A 1 carat ring, or 2 carat diamond, or 3 carat diamond. That's the weight there. Okay, and a carat is equivalent to about 200 milligrams. So it's based upon the weight. And so the weight plays a big factor in the value of a diamond. But that's only one of the things that you use to decide how valuable a diamond is going to be. Okay, so if you ever go ring shopping for somebody, they'll teach you about the C's that are all important. Another one that's important is what they refer to as the clarity. So let's take a look here. So in these two pictures, here are two diamonds that are the same size, perhaps the same weight, but you notice that on this one you have these kind of spots in it, right? It's not as clear as what's over here. It's like a little smudge on the inside, a little smudgy on the inside. So these places here are part of what we talk about when it comes to clarity or having flaws. So that's one of the other C's, is clarity. And the clarity is referring to how many flaws are on the inside of a diamond. You don't want any flaws because it loses its brilliance. It's not as bright that way, and so you lose what it looks like because of the lack of clarity. So for these two images here, this one with fewer flaws, which has a greater amount of clarity, is going to be of a greater value than this one here. They can have the same exact weight, but this one is going to be more valuable because it has less flaws. So now, in using that information, let's take a look at the next activity. The next activity is based upon various types of diamonds and their weight and their actual price and their predicted price. And so we can see right away that we have a chart. The nice part is it's organized for us. We can see it's going from smallest to greatest. And we can see a couple of things. We have 4 different 1 carat diamonds, but notice that the predicted amount for those is all the same, right? $4,429, but the actual price is going to be different. That actual price has a lot to do with those other values we talk about, things like the clarity or the flaws you have in it. Other things they look at are going to be color and things like that as well. So, but for now we're looking at kind of clarity. So based upon its weight, you would get this amount, right? Based upon the weight, you would think you get that amount, but because of the flaws that are going to be in it, you might get a difference there of how it comes out to be. And you can see this is true for all the numbers here. Here are 2 that are predicted to be 4,700 apiece, and one is 3,900 and one is 4,400. Both are less than what the prediction was going to be, but one is substantially less there. Here's another pairing here, the 1.5s, right? And you can see that with these 1.5s, this one ends up being worth more than what they predicted. This one's far less than what that one predicted. So you could have a 1.5 carat ring and another one, and they say, well, it's the same carat size, but the value of that diamond could be substantially different. This is about a $1,500 difference there. So that's what the chart is showing us. All right, let's take a look at the questions that go with this here. It says the scatter plot shows the prices and weights of the 20 diamonds together with the graph of y equals 5,520x minus 1,091. So this scatter plot are the 20 diamonds just scattered here, with the weight being the independent value here and the price being dependent on the weight there. And they give us a equation here, and this equation creates this line that we see right there. Okay? The function described by the equation y equals 5,520x minus 1,091 is a model of the relationship between a diamond's weight and its price. So this equation here is a model that helps us understand the relationship between 2 items, the weight and a price. The purpose of the model is to do what? To predict the price of a diamond from its weight. So if you have an accurate model, you can predict what a diamond is going to cost based upon the weight. These predicted prices are shown in the 3rd column of the table. So using this equation here, these numbers are generated. So when you take the weight of a carat and you put it in the place of x and you multiply it out, 5,520 times 1 minus 1,091 would equal $4,429. That's what you would predict would happen. So when it says that 2 diamonds that both weigh 1.5 carats at different prices, what are their prices? Well, let's call this one A and this one B. For A, the price for A is actually $7,474, and the price for B is $5,904. So there's a difference there in those 2 values. So how can you see this in the table, and how can you see this in the graph? So in the table, we can see it here, and we can find the 1.5 and see the value. There's the predicted value and the actual value there. On the graph, where do we see the 2 1.5 values? Well, we look here. Here's 1.5, and we have one of them right here at a cost of, that's lower than 6,000, so this must be B. And we have this one right here, which is close to the line above 7,000. This would be letter A. So we can see them there on the graph, no problem, and we saw them on the table. This model predicts that when the weight is 1.5 carats, the price will be $7,189. How can you see this in the graph? Well, on the graph, where is this value in the graph? It's what it's asking you. Where do you see this value in the graph? and we see that value in the graph at the place where the line is at. So the line where it crosses, that is where we are at $7,189. In terms of the equation, the place where we would see that value is going to be in the predicted price here. We would see it right there. That's where we see it in the table. But it's pretty nice to look at a graph like this because you can tell, is this diamond worth what it should be? This one here should be worth more, but there's something wrong with it, which means its value is less. Same for these ones over here. Some of these other ones, their value is worth more than predicted, probably because it's just a better diamond than what they anticipated it being. Okay? So that's the idea right there. In terms of the equation, we can also say that, again, the equation would say that y equals 5,520, and then we put 1.5 as the weight value of x minus 1,091. So when you work that out, what do you end up with? This becomes 8,280 minus 1,091. When you subtract there, we end up with 7,189. So that's how the equation also shows you that same information. All right, kind of handy. When you keep looking at the same thing, number 3, it says one of the diamonds weighs 1.9 carats. What does the model predict for its price? Now the model is the what? The model is going to be the equation that helps us do that, which is column 3. And then how does it compare to the actual price? We want the predicted price and the actual price. So the predicted price for the 1.9 carat, come down to our table, is $9,397. So $9,397. The actual price of that diamond, because of flaws or whatever else it might be, was $9,541. $9,541. So how does the prediction compare to the actual? The prediction was actually what? It was less than the actual value. Okay, so the prediction had it coming in less than the actual value, so it was a little bit under predicting in that case there. Find a diamond for which the model makes a very good prediction of the actual price. How do you see it in the table, and how do you see it in the graph? Okay, so where are the prediction and the actual close together is what we're talking about. So let's take a look here. We could look first of all at the table if you wanted to, or you could begin with the graph. Up to you what you want to look at. I started in this one. I said let's look at the graph, because when I look at the graph, if it's a good predictor, it's going to be right on the line. And so for me, I saw this point right there, which is somewhere between 1.14 and 1.26, right? It's right there. So maybe somewhere about the 1.2 range. So I know I'm looking for something in about the 1.2 range. So when I go on my table, I see one right here at the 1.2 range, and we see the predicted and the actual. And what's the difference between these two values here? We have 5,544 minus 5,533. The difference there is only $11, meaning that the predicted price was only $11 less than the actual price there. So this one, the 1.2 carat diamond, is the one I would say is a pretty good one to take a look at. And we can see that in the table, and we can see that in the graph as well. I'm not going to write anything here because we can't talk through it. Then it says, number 5, find a diamond for which the model's prediction is not very close to the actual price. So one where it's way off. And then again, where do you see it in the table, and where do you see it in the graph? So I like looking at the graph first of all, and what I would do here is to try to find one that's not near the line. One that doesn't seem to be where it should be. So, I got a couple. This one's not near the line. This one here is also not near the line. So if I pick this one right here, for example, way out there, this is somewhere between 1.9 and 2.1, so somewhere in like the 2 range. So now let's look back and say, well, where's a 2 range one? I have the 2.04 right here. Now it should have been $10,170 in its value, but it ended up only being $9,125. So the difference there was it was off by, in this case here, $1,045 less than what it should have been, right? That's a big difference. So it should have been worth $10,000, but it was only worth $9,000 because of the issues that it had with it there. So that's an example for one where the prediction was not very close to the actual price. right? So I would use the 2.04 model, and that's what we talked about there. All right. In the next activity, it says the agony of feet. We have a scatter plot here that shows the lengths and widths of 20 different feet. And what I want you to begin with here is take a look at these lovely feet right here, and really just kind of look at what you have and say, what do you notice, what do you wonder about these 3 feet? A couple things you might notice is they all are the same length, but they're all a little different in terms of how wide they are. This one's pretty wide, kind of a medium, and what we call narrow. So while the foot length is the same for A, B, and C, we notice that they have a different width, because not all feet are the same width, nor are they all the same length, right? Okay, so we have a variety of feet here. And we use that same variety in this scatter plot here, which shows various lengths and widths of 20 different left feet. All right, so we have the foot length here and the width there. All right, so as the foot length seems to, what do we notice kind of a little bit? We notice as the foot length seems to increase, the width also seems to increase a little bit, right? We have some ones that just don't quite fit in, they're way out here. But let's take a look at the questions that go along with this. Now the first question here says, estimate the lengths of the longest foot and the shortest foot. So let's take a look and find the longest foot and the shortest foot and figure out where the lengths are going to be. So our foot length is here. Our longest foot is there, which has a length just a little bit more than 30. And our shortest foot is somewhere about here, which has a length a little less than 22. So you might say 30 and a half, and this one might be 21 and a half. So our longest might be 30 and a half, and this one might be 21 and a half, and we're talking about centimeters. Again, just an estimate there. How about the estimate the widths of the widest foot and the narrowest foot? All right, well the widest is going to be up here, which this is still the widest foot, so that's almost 12, so maybe about 11, 0.75, I'm not sure, just estimating. And then the most narrow foot is right here, one furthest down. That's our narrowest foot, which is at about 7.5. Just based upon where we find that dot for the foot length, smallest to widest, or narrowest to widest, that's our most narrow, and here's our widest. So we would say 11.75, and then we said 7.5 here. Again, just estimates. If you got different numbers, that's okay. If your teacher has different numbers, that's okay. We're just estimating. So here's the same scatter plot with the graph of a model for the relationship between foot and length. So the graph of the model means what? We're adding this line right there to show the relationship between foot length and width. And that's what that line is showing you there, the relationship between those two elements. All right. So then it says, okay, great. This is kind of like what we would expect, a little bit like for the diamond. Based upon the weight and the price, we would have an expectation of how much it would cost based upon how much it weighed. So our expectation for a foot length is, if the foot length is somewhere around here, we would expect the width to be somewhere around there, right? So if I picked a point, and let's say I picked a point at 20, let's do a foot length of 28. If I had a foot length of 28, I would predict that it had a width somewhere about 10.75. Right? Again, I'm just making up a number here, just estimating, showing how this graph of a model helps you make some predictions. Then it says, circle the data point that seems weird when compared to the model, meaning which one doesn't quite fit, which one just seems out there. And the one that doesn't fit at all seems to be this weird one right there. That's our weird one. Now, where is it? Right? Well, it's a little bit more than 24, so maybe 24 and a fourth, or 24.25, I don't know. And in terms of the width, we would say it's about maybe 7.5. So, what does that represent? It represents a foot that's a little more than 24 centimeters long and 7.5 centimeters wide. Now, when it's way out here and a little bit weird, in math terms, we call that an outlier, meaning it's outside all the rest. All the rest really do a good job of fitting inside of here, right? And sometimes people talk about this as being like your hot dog bun, and you want the hot dog to be in the middle of the hot dog bun. So when you do this, there's my hot dog bun and my hot dog, this one is just not working out. It doesn't seem to belong. It's an outlier. It's weird. And we usually just don't consider that as being part of like the normal stuff. When you're doing data stuff, often you throw that one out and say, don't count that one. That's just weird. It's not part of the norm. Okay, so that's really it. Let's take a look at your summary then. Summary, there we go. So sometimes we can use a linear function model of the relationship between two variables. So we can use a linear function model as a relationship between two variables. So here's a scatter plot talking about the height of dogs and the weight of dogs. And the graph of the linear function shows the relationship between those two things, how one is connected to the other, and vice versa. In this case here, it's not so much about independent or dependent, but they are showing a relationship and how those are connected. We can see that the model does a good job of predicting the weight given for the height. So it's doing a good job predicting those things. Okay? Now sometimes the model might over-predict the weight of the dog, and sometimes it might under-predict the weight of the dog. Okay? So in this case here, the model would show that these ones here are under-predicting, in that case here, but actually this would be over-predicting, sorry. This is over-predicting, because you can see that the line is over where they are, and this one here is under-predicting, because the line would say it should be here, but it's way up there, so it under-predicted, because you would think a 27-inch dog would weigh 80 pounds, but actually it weighs 112, so we under-predicted. Okay, so that's what happens there. And again, things that just don't fall on that trend, not part of that line, they don't fit on a trend line, those are referred to as outliers. All right, we're going to pause there and let you have some time to work on your homework. We'll come back and check that again in just a few minutes. All right, homework time. The scatter plot shows the number of hits and home runs for 20 baseball players who had at least 10 hits last season. The table shows the values for 15 of those players. So we have 20 dots here, and we have 15 players over here. The model is represented by y equals 0.15x minus 1.5, which means this model is what we use to form that, or create that line right there. All right. Use the graph and table to answer the questions. Player A had 154 hits in 2015. So where do we see 154 hits? Oh, we see it right here. Here's player A. How many home runs did he have? In this case here, he had 26 home runs. 26 home runs. And how many was he predicted to have? Well, he was predicted to have 21.6 was what his prediction was supposed to be. That's what we have based upon the numbers that were given. Okay, can we see that guy in the graph anywhere? Sure. We can see that with 154 hits, somewhere over here, that the home runs that he had was 26. So we're looking for one that's about there. This one here looks like player A. It's just between 20 and 30 and over 150. Player B was a player who most outperformed the prediction. Outperformed it. So he did better than expected. How many hits did player B have last season? So who had more hits than expected? This is our expected line. So people that had more than what were expected are going to be above the line. We have one here, just a little there, and one here, and one here. So who was the most over the line? I would say, based upon the length of these lines here, I'd probably go with this one here as being the most over the line. This person. So who is that person? Who is player B? We see his dot, but where is he in our table? Well, let's take a look. Player B is going to be somewhere over 50 hits, right? So you have 50 plus hits, and in terms of home runs, it's somewhere in the teens, maybe about 15 home runs. Something about that we're looking for. So where do we see 50 hits, about 50 hits, and 50 home runs? Here's 57 hits and 3 home runs. That's a little too few. and then here's 57 hits and 16 home runs. That makes the most sense. That's close to our prediction, so this is going to be player B right there. This one right here fits that one right there, doesn't it? 3 home runs. That person underperformed. This person outperformed. What would you expect to see in the graph for a player for a player who hit many fewer home runs than the model predicted? Hit many fewer. That seems weird. So, person who hit fewer home runs than predicted. Let's just go with that. So, what would you expect to see for someone who hit fewer than predicted in the model? Well, the model's here. We would expect to see, if they hit fewer than was predicted, we'd expect to see that their dot would be below the line, right? So these guys underperformed right there. That's what we would expect to see. All right, number 2. Here's a scatter plot, it's on my next page, that compares the points per game to free throw attempts per game for basketball. So, in a tournament. Now here's what we have. Points per game and free throw game, scatter plot showing how those relate. The model, represented by the equation y equals 4.413x plus 0.377, is right here. Its graph of the scatter plot. X represents the free throw attempts per game, and y is the points per game. Circle any data point that appears to be outliers, meaning it's just not close to the line. Well, the ones that are the most outlier for sure, this one here is definitely an outlier, right? It's way out there. This one we might say is an outlier. It's a pretty good distance from that, but maybe not quite as much as it might be. This one perhaps is an outlier. That's a maybe, but I would say definitely these two are outliers. This one is kind of close to being an outlier too, right? But it's not going to be perfect. So this is where you have to kind of estimate a little bit what's going to be an outlier. Those two are the furthest away, so that one's a for sure. This one's a maybe. I probably would say those are okay. They're close enough. So what does it mean for a point to be far above the line in this situation? Well, in this case, if I'm far above the line, it means that I made more points than I was predicted to make. You see, if I had 3 free throws, I'm predicted to make only about 12 points. But if I'm up here, I make 22, I made more than what was expected. So to be above the line means that I made more points than was predicted by the number of free throws. So I made more. There's an increase there. Again, I'm not going to write that out. I'm talking it through. You can write that out yourself. Based on the model, meaning based upon our equation, how many points per game would you expect a player who attempts 4.5 free throws to have? Well, 4.5 is here. So how many points do we expect this person to have? We would look over this way, and they'd be right about here. So I'm between 15 and 22.5. So if we're kind of thinking about this being a distance of 7, halfway is 3.5, that's 18, a little more, maybe 19, 20. We'd probably say somewhere about 20. Okay, it says round your answer to the nearest tenth of a point. Again, you're just estimating. So somewhere near 20, 20.2 points per game. Points per game. Again, just estimating there. One of the players scored 13.7 points per game with 4.1 free throws. So 13.7 points, which is about here, and 4.1 free throws, which is here. So we're talking about this person right there, that person, okay? How does this compare to what the model predicts for the player? All right, the model said they should have had more points. So this player actually underperformed compared to the model, because the model said that they should have had somewhere up here, maybe about 17 or 18. They should have had about 17 to 18 points, and instead they only had 13.7. So they did not do as well as they should have done there. Another thing we could look at, again, the model that's based on the graph. Based upon the model, I should be more clear here, you want to use the equation. So let's take a look here. If we do 4.413 times the free throws, 4.1, and we add that to 0.377, this becomes 19.8585 plus 0.377. When we add those together, we end up with 20.23555. And again, looking at kind of nearest tenth there, we would say that's where we are there. Okay? So I should have done the same for C as well. I should have done that as well. I was estimating. So if I put in 4.5 based upon the model, so sorry about that. I forgot what I was doing there. Oh, sorry, this is 4.5. 4.5, looking at my notes. If I use this for the 4.5 model, I get 20.2. If I do this one based upon the model, then I'd multiply by 4.413 times 4.1 plus 0.377. Okay, so I do that for this guy there, and when you work that out, you'll see how much they underperform by. It should be somewhere between 17 and 18 points. All right, that gets you close enough for now. You're good for that one. Have a great day, and we will see you next time.